Okay, hi everyone. Well, this is the beginning of a new series that I'm looking at about history of science and technology, Q&A about history of science and technology. And I'll talk about anything I know about. I haven't quite figured out what my principles are going to be about talking about living people and what kinds of things I can say and can't say, but I'm going to kind of, let's see, I'm going to talk about a bunch of different things. Now, actually, one question that had come up in an earlier live stream today about software design was a question about the history of LISP. Maybe I can start by talking a little bit about that. I'll talk a little bit about the history of programming languages in general and the history of LISP in particular. So, when did digital computers come into existence? Well, you know, things like the ENIAC were around 1946, I guess. We talk about the prehistory of those things. That's sort of a separate topic. But when there started to be computers, they started to have these sort of well-defined modules of operations that they could do. And there slowly started to be stored program computers where you could like specify the program, but the program was very much like, make the addition module do this, make the this module do that. It was very direct, instructions to the different pieces of the machine. And then there slowly started to be, in the 1950s, there started to be kind of a let's write kind of what was originally called symbolic languages, I think, but they were really languages that tried to not go all the way down to the details of which particular storage location in the machine should do which particular thing. And the two very early languages were Fortran and COBOL, both around 1956 to 58, I think. One of the things that people were very obsessed with at that time was what would like the grammar of the language be? Like strangely, in 1956, there was sort of a convergence of two completely different threads of intellectual development. And I'm just amazed that they happened in the same year. One of them was the this thing now called Backus-Naur form, which is this kind of recursive specification of the structure of a computer language. And the other was Chomsky's generative linguistics, generative grammar approach to natural language. So just talking about both of those for a moment, the question is, if you're going to say, what is a possible word, what is a possible thing that can appear in a computer language? It might be something like, oh, we've got expressions of the form blah plus blah. And the blahs can in turn be parenthesis blah plus parenthesis, blah times blah. And what we're saying is when I say blah, that blah is sort of a recursively defined thing, because the blah could itself be an addition thing, a multiplication thing, a thing with parentheses. So you can write that all out as a kind of a description, a kind of a specification of the grammar of the language by saying blah can be blah plus blah, or paren blah paren, or blah times blah. And then at the bottom you can say, or blah can be like a number or something. And so that's a sort of recursive definition of that can be used to specify the syntax of a computer language. And that's what Backus-Naur form was about for computer languages. Strangely, at the same time, Noam Chomsky had come up with this generative grammar idea. I think that had some precursors in, you see, this is going to be one of these problems with this history. Oh my gosh. Noam Chomsky's kind of undergraduate advisor at University of Pennsylvania. I lost the name, sorry. But there have been some precursors to that. But for many, many years, people had had written grammar books and so on, but they hadn't really been formalized like that. And there hadn't been the idea that there could be a procedure for like generate all the sentences of such and such a language. Now, actually, as is often the case, that idea had a precursor. There was a grammarian called Panini who did a grammar of Sanskrit. I'm not quite sure when, maybe a few centuries BC. And it was even known to people, in antiquity, in Greek and Latin, there was a decent level of knowledge of kind of the structure of grammar as a formal thing. People like Lucretius commented on it as actually a possible theory for how physics might work. In the 1st century AD, Lucretius was talking about how, the world might be made up of things much as sentences are made up from words according to a certain grammar. In any case, 1956, these two different lines of development converged. There's a question here: Do I know Noam Chomsky personally? I've certainly met him. I've actually asked him about what happened in 1956. I didn't get a lot of clarity about that from him. I think that my impression was that he was aware of the work that was going on in computer languages. I'm not sure how aware the people in computer languages were of generative grammar, so I don't really know what the historical chain was there. I think that okay, so we're back to the kind of the development of computer languages. Fortran, COBOL, two early languages which have survived. There were many others that did not survive. I think both of those languages, I think, had a certain degree of, IBM was sort of the dominant computer company of the time, and that was, those languages certainly had involvement with IBM. But people had, that was sort of in the development of practical computer languages. That's like you write this program and it actually runs on the computers that exist at that time. There was also the more theoretical development that had come out of things like Turing machines. Turing machines invented in 1936, lambda calculus invented basically at the same time. The idea of recursive functions was actually a little bit older. Kurt Gödel had used general recursive functions in his proof of Gödel's theorem in 1931. A recursive function is a function where you define the function in terms of itself. So you might define a factorial. F of n is defined to be n times f of n minus 1. So f of n is defined in terms of another instance of f. It's the same idea as with these recursive definitions of grammars, same basic kind of concept. But recursive functions were known to be one of the possible bases for doing computation. All of these different bases for computation were known to be equivalent. That was already known by 1940-ish. But then the question was, would there be a way in which those kind of theoretical bases for computation entered the world of practical computers? And it really didn't happen very much. One of the big things that happened heading towards 1960 was the creation of Algol 60. Algol was intended to be a committee made, the experts of the world will come together and define the be-all end-all language for computing, and it was going to be Algol, the algorithmic language type thing. Algol 60 was for the sort of 1960 edition of that. In the end, Algol wasn't really implemented much. I'm not even sure there was ever a complete Algol that was made, but Algol was very influential in terms of defining sort of what the typical programming language might look like. And in fact, basically most standard low-level programming languages are very Algol-like even today. But there was there were sub-branches to that, and Algol was very much a story of use this Bacchus-Naur form to represent the syntax of the language and so on. And there was really an emphasis on sort of the syntactic structure of the language and on how there was the idea of having variables where you could set a variable to something and that would correspond to actually putting a value in some particular location in computer memory, where the particular location will be decided by the compiler of the language and so on, and the loader and such like. But by compiler, I mean the program that turned the sort of high-level Fortran code into the actual machine code of the computer on which it was going to run. But one kind of outlier, there were two important outliers. One outlier to that story was the Lisp language, which was kind of originally proposed as let's take the idea of recursive functions and try and see whether we can make a practical language along those lines. And the person who proposed it was a chap called John McCarthy. And his original proposal, I guess, was around 1959. In fact, the idea was, let's take something quite formal, quite, Algol had also been quite formal, but Algol was more concentrated, I would say, on the syntax than on the semantics of what was going on. Although that may be a little unfair. I haven't read the Algol standard in a very, very, very long time. But in the case of what John McCarthy was doing, the idea was this would be a thing that sort of implemented recursive functions. Well, one of the questions was, how should he actually set up the representation of recursive functions? And he was aware of Alonzo Church's work from 1935, 1936, then 1940, and so on lambda calculus. And that was, and the way that he chose to set up functions was sort of in some imitation of lambda calculus. Actually, he was also, as I realized only very, very recently, also aware of Moses Schoenfinkel's work on combinators from 1920, which had the notable feature that it didn't have to deal with variables. See, one of the things, and let's not get into too much of the technical details of this, but it's sort of the bane of a lot of computing is you want to name a thing, you call it X, but you use it in you have this thing, you've called it X. Now you have another thing, and you independently name it. And by the way, you happen to call it X. What happens? And how do you scope the names X and what they refer to? And that's a very complicated issue. That it's not clear, it wasn't clear when lambda calculus was first invented, it wasn't clear you could ever untangle that issue, or whether these names would get forever tangled up and prevent you from proving useful mathematical theorems and so on. Combinators are much more difficult to understand, and were invented before all of these things, but had the feature that they don't involve variables at all. They just deliver data to the right place by having the sort of transformations of symbolic expressions, and they never have to name anything. Well, the good news is that means you can prove all kinds of theorems. The bad news is us humans are pretty lost in figuring out what's going on. We don't have a way. It's like if I were talking about things in language and I were just saying the blah and the blah and the blah and the blah, 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 etc. And I never fill in what blah means until the very, very, very end, when it's like dog, cat, etc., etc., etc. They're going to be filled in for those things. It's very hard to understand that without the kind of intermediate sort of separately understandable thing. But anyway, John McCarthy, I recently learned, also was aware of combinators, and sort of says it even in his paper. I just found this recently. We could use combinators, but they would be very obscure. And so we're going to use this thing that's sort of modeled on lambda calculus. Now, what happened to Lisp was, at the time, there was sort of toy versions of Lisp that started to be implemented, but fundamentally, it was really hard to implement on the machines that existed in the early 1960s. Those were primarily mainframe computers. That was sort of the IBM 360 was the quintessential mainframe computer, and it was kind of like the notion was they were big computers. I mean, I used one. It was it was the size of a room, and it was in special air conditioning. And usually, I was very lucky. I worked at Argonne National Lab in the summer of 1977, and it was a place where they trusted the scientists, so to speak, and even the kid scientists like me, to actually be in the room with the mainframe computer. So I actually got to kind of touch the machine, so to speak. In most other places, it was just only the people behind the scenes, possibly even wearing white coats, would be touching the mainframe computer, and the simple users will be just putting card decks in pigeonholes, and somebody will be taking them from the other side of the pigeonholes and going and mysteriously doing things on the computer and then delivering the printed output back to the pigeonhole, so to speak. But anyway, so but the IBM 360, and I think actually it was probably a precursor to the 360, maybe 801, if I remember correctly. I've forgotten. That famously had the instructions car and coulda, which became actual sort of language instructions in Lisp for what are they? They're prepend and rest, I suppose, in Wolfram language. I think that's right. But so okay. So anyway, Lisp was kind of a gosh. There's so much to say about this, and it's hard to know where to start. It was sort of a good conceptual idea. It was hard to implement, and it didn't get efficiently implemented really, until quite modern times. You know, one of the things that's often said by people who were involved with Lisp is, you know, they would say, thinking it to be, well, I don't know, but you know, every sufficiently sophisticated programming language will eventually recreate Lisp. Well, welcome to the universal computation. That's sort of inevitable. It's you know, every sufficiently rich computational environment will reflect every other computational environment at some level. But in any case, the characteristic of Lisp was that it's the syntax, going away from the kind of obsession with syntax that was in lots of other languages. You know, the original version of Lisp was just a bunch of parentheses, nested parentheses and things, not kind of functional notation of the kind that we would normally use in math or in Wolfram language or in programming languages and so on. And actually in John McCarthy's paper, he says, well, we're going to use this S expression form that's just these nested parentheses for now, but there's an M expression form which looks bizarrely similar to Wolfram language today that we'll get around to at some point. Actually, I remember talking to him about that, and he said, well, yes, back in 1959, we thought we'd get around to it very, very soon. But I was talking to him sometime probably in the maybe 1990s or early 2000s, and hadn't gotten around to it yet by then. But in any case, you know, Lisp was kind of promoted as the language of artificial intelligence. And in the early 60s was a time when there was just tremendous enthusiasm for artificial intelligence. It was like, we've made computers, pretty soon they're going to be just like brains, and we're going to be able to do every intelligent thing that brains can do. And it was sort of interesting because before that time, I would say that was a growing sort of tide that happened from the mid-1950s up until the 1960s. Like, for example, in 1956, there was a sort of famous conference. I was just looking at the proceedings of it, actually, just a couple of days ago, interestingly enough. It was a conference in Dartmouth, 1956. The proceedings were edited by Claude Shannon and John McCarthy, and it featured Marvin Minsky and lots of other sort of people from the early days. I think Michael Rabin might have been in that. A bunch of people from sort of the early days of kind of thinking about theory of computation and its application to practice. But, you know, I think John McCarthy's paper in that, as I recall, was something about the inverses of Turing machines. It's definitely not a kind of sort of a practical computer language thing. And a lot of what's in there is kind of, can we make a Turing machine, really a Turing machine that is somehow intelligent now, or somehow has artificial intelligence. Now, part of the segue to that had been the work by Walter Pitts and Warren McCulloch in the 1940s on early neural nets. I mean, they had kind of, that was a time when, I don't know, psychiatry was sort of the top field in some sense, the really expanding field at the time. Warren McCulloch was a psychiatrist based in the Chicago area. Walter Pitts was a young kind of funky background fellow who sort of wound up at the University of Chicago as sort of a math and what today would be a sort of computing prodigy type. But those two kind of, Warren McCulloch kind of wanted to find this sort of mathematical idealization of the way that brains work, and it had been known since Ramani Kajal in around 1900 that there were neurons in brains. They'd done the microscopy and drawn these beautiful pictures of all these elaborate neurons that looked awfully like the wires that people saw inside computers back in the 1940s and so on. And so there was the obvious question, you know, could we make a kind of wires-like model of how brains work? It was known by that time that it'd been known for a long time actually that that brains were sort of electrical in their operation. I mean, it was known even when Volta was discovering, you know, you can make a frog's leg kick by connecting it to some electrochemical battery type thing. It had been clear that there were kind of electrical signals involved with nerves. So anyway, but back in 1943, I think, Walter Pitts and Warren McCulloch wrote this paper about neural networks, that was sort of an attempt to idealize away from the details of neurons and come up with something more mathematical, so to speak. And one of their sort of key ideas was, and let's see if we can show it's equivalent to Turing machines. Because then they had the idea, if it's equivalent to Turing machines, then it's equivalent to lambda calculus, it can compute all these things and so on. So that was kind of a connection between kind of the world of the world of sort of intelligence and brains into this kind of, and it might be like a Turing machine type thing. And that led to, particularly at that time, there's a lot of work on finite automata, things where you have a finite number of states and you say, it's like an elevator or something, which might have a state that says the elevator is going up, the elevator is going down, a button is pressed, that changes the state, that does, et cetera, et cetera, et cetera. Just these state transitions and so on. The theory of finite automata was kind of big in the 1950s and got more or less figured out in the 1950s. And I think that the thing that and Turing machines are sort of, they're not finite. They have tapes that can be infinitely long, so they can store an infinite amount of information, and that kind of brings them into another class of computation. But sort of the first idea was, could brains be kind of modeled like finite automata? And then there was, okay, then what about Turing machines and so on? But in any case, this sort of all converged, I think, into this kind of, can we do artificial intelligence? By the way, it also was the case that often people would refer to computers as sort of things like giant electronic brains. That was the kind of 1950s style, popular name for what a computer is. It's like a giant electronic brain. And there have been things which were sort of very, very toy examples of artificial intelligence. I think there was a chap called Gray Walter who made this turtle-like thing, was sort of a hemispherical turtle, was made for the World's Fair in the mid-1950s, I think, New York World's Fair, maybe. And it was a thing that had sort of motor inside it. It would run around on the ground, and it would follow white lines on the ground and so on, using photodiodes probably. And it was kind of the original model that led to things like the logo turtle and nowadays the scratch cat and things like this. But it was this kind of turtle running around on the ground. And it actually, at the time, it was a pretty famous turtle. It made the cover of Time magazine and all those sorts of things. And it was like, will every home have one of these, robotic turtles running around? Well, actually, lots of homes now have robotic vacuum cleaners, which look strangely similar to that, but it came through a long series of technology development to get to that point. But anyway, so there was this idea that, artificial intelligence, giant electronic brains, easy to do, going to be on their way real soon now. And that was an idea that, and then there were sort of questions about, well, how would you get to that point? How would, what would be the immediate things you would try to do? There was things like object recognition. Okay, so visual object recognition. People had, you could have a small array of pixels, and there was a question of, could you recognize things by just looking at these pictures with a small array of pixels? There was a chap called Frank Rosenblatt at Cornell who invented these things called perceptrons, which were kind of a way of using what amounted to kind of sort of thresholded linear algebra to be able to say, you take the inputs from all those pixels and you compute this function, and then you say, is this function closer to this or closer to that? If it's closer to this, then it's a cat. If it's closer to that, then it's a dog. And so that was an early kind of approach to sort of a pseudo AI thing. Now, things went kind of wrong because, you would do very, very simple training of perceptrons, and there's a famous example with recognizing tanks, pictures of tanks. And it was like, oh, well, we're training it on this set of tanks and this set of pictures and so on. It turned out, really, in the end, the perceptron was just recognizing whether the picture was taken at the day or the night. And it wasn't really recognizing much about tanks at all, but it wasn't obvious that was what was going on, because it was just like, well, we got this training set, and this was in the 1950s, so maybe 1960 by then. So it was kind of it's interesting that same issues come up in machine learning today. Nothing really changes. By the way, at that same time, people were starting to use two-dimensional cellular automata to do things like optical character recognition. That was already starting in the 1950s. And subsequently, neural nets got used for that. It was a very early application of neural nets. But in any case, let's see, where was I? We were talking about AI. Other applications of AI, there were things like, the one was was things like medical diagnosis. There are all these different paths for, you ask this question, could it be this, could it be that? It's kind of like the 20 questions version of medical diagnosis. Which of the 100,000 things in the ICD-10, medical diagnosis codes list do you actually have? Well, do you have a sore throat? Do you have this? Do you have that? Make those choices. That question, well, that led to a system called Dendral, which was kind of a tree searching system, and somehow that related to also early studies of theorem proving. It's related, but I don't. Yeah, okay. So I mean, in theorem proving, what you're doing is you're saying, I have these axioms, and I can make these moves to change mathematical expressions. Which sequence of moves should I make to get to this answer? That's kind of what you need to do to sort of prove a theorem in this kind of idealized way. Strangely, it's also very similar to the question of what do I need to do to synthesize a particular chemical if I have certain chemical reactions that I can do. And even in the 1960s, people were exploring, I think E.J. Corey at Harvard was already exploring, famous for retrosynthesis and other such things, was already exploring these ideas about using sort of theorem proving-ish methods to chemical synthesis. I think there was a big effort at Stanford, I think around Dendral. I think Joshua Lederberg was involved with that. I remember talking to him about it many years later, and asking him, why did nobody follow up? Why wasn't there a big effort in sort of automated medical diagnosis? And he says he didn't really know. Should have been. There wasn't. As Joshua Lederberg was a microbiologist latterly at Rockefeller University, and I think was famous. One of the things he was perhaps famous for to some people is he was the person who convinced people that when the Apollo astronauts came back from the moon, they should be in quarantine. Feels a bit like today, because just think about what moon bugs they might have brought back. We didn't know. So in any case, the thing that so back in early 60s, these various initiatives of sort of treeing out of things and theorem proving, maybe in medical diagnosis, that was one kind of approach. There was also kind of the idea that if you wanted to understand AI, you could sort of look at these simplified situations. You could look at this kind of world of blocks, and you could say, if you just had to figure out how could you put this block on top of this block, and how could you plan what to do, how would you do that? It later turned out that was a fine model for understanding sort of mathematical style optimization problems. It wasn't a particularly good model for understanding the things that nowadays we think of as being the sort of mushy, AI-ish kinds of judgment type things. Another direction was in natural language processing. And in particular, there was this great interest in language translation for a very bizarre reason. I mean, this was the height of the Cold War, 1962, the Cuban Missile Crisis, all these kinds of things. And there was this idea that, there would be these high-level talks between the Soviets and the Americans or whatever. And, one of the weak links, it was thought, was the interpreters who were, translating Russian to English, whatever else. What if one side said, we will allow no missiles in Cuba, and the interpreter mistranslated that to, the beaches in Cuba are wonderful or something. That might start World War III. And so the bright idea was had by the then, it was probably ARPA at that time, as opposed to DARPA, the part of the Defense Department involved with advanced research projects and so on, that I think they already existed at that time. Yeah, that gosh, the way to avoid human error would be to have a machine do that translation. Let's really push machine translation. Now, of course, we now know machine translation was a lot harder than people expected, but that was another big push in the 1960s. And really, this whole, a whole collection of things, sort of automated mathematics, automated language translation, all these kinds of things, they all kind of were the big story of AI in the 1960s. And underneath, the more symbolic of these, the ones that involved things like making deductions about things and so on, LISP was the thing that was kind of the story of how you should do that. Well, Then we come to the late 1970s, when I started working on symbolic computation and trying to build, well, precursors of Wolfram language. I built this thing called SMP starting in 1979. I did the shocking thing. I built SMP using the C programming language, not using Lisp. Why didn't I use Lisp? Because I didn't really need to. Lisp was at that time not well implemented. It didn't run fast. It had all kinds of problems with memory management. And I knew that the basic operations I needed, I could implement quite easily, and I could implement them in sort of the form that I wanted, which, as it turns out, is this idea of transformation rules of symbolic patterns that transform symbolic expressions, which has for the last 40 years been an extremely powerful paradigm that we've been able to use in Wolfram language that isn't really the paradigm of things like Lisp. It's a little bit similar, and you could obviously write a pattern transformation system in Lisp, but it wasn't what Lisp naturally did. And it made a lot more sense for that to be something that was written directly in C, which was at that time a new sort of low-level program implementation language that had been built basically for the creation of the Unix operating system at Bell Labs. But anyway, so that was I must have run into John McCarthy for the first time, probably around the time I was working on SMP. And he did not like the fact that I wasn't using Lisp. This was an AI-ish application and it wasn't using Lisp. And I think that led to a kind of I would say a rather negative vibe with John McCarthy. I mean, I can, oh gosh, I remember this must have been, was it 1981 maybe? 1982, I can't remember. I was at Caltech, kind of being a young physicist there. And I was, can't remember exactly what the precise situation was. But anyway, I was like, eventually I ended up moving from Caltech for reasons having to do with the first company that I started and all kind of intellectual property issues and so on. But anyway, I was sort of on a job search type thing. And I had decided Stanford was the place. The climate was nice. The environment was nice. I kind of liked the area. It seemed like, Silicon Valley was nothing really yet, or very little yet at that time. But I just sort of seemed like a nice place. And so I was like, okay, I'm going to see, if I can get a job at Stanford. And it turned out that I was at that time doing a bunch of particle physics. It must have been like 1981. It can't have been too much later than that. So the Stanford Linear Accelerator Center, which was a sort of particle physics lab, was keen to get me to go there, in the Stanford physics department and so on. And then it was like, but I'm also interested in computer science, and okay, you should do something with the computer science department as well. So I remember I went to lunch with the computer science department, and there's a whole bunch of people there. And you got to remember that this was a time before the web. So, I didn't have the list of who were all the people in the, today, if I'd been going to visit that department, I would have said, who are all the professors in that department? Who are all these people? What are their stories and so on? But in those days, that was not an easy thing to find out. And so, I just showed up there. Showed up to lunch, and there were people like a guy called Ed Feigenbaum, who was much involved with artificial intelligence at that time, and a whole variety of other people who I'm not immediately remembering. But there was this one chap, this white-haired chap. You go around the table and people are introducing themselves and so on. And he says, "My name is John Smith." It's like, okay. It seemed implausible. That's to people, at least from the UK, the name John Smith is kind of the John Doe of the US. It's kind of the generic name. And it's like, okay, it seemed unlikely, but I don't know. And that kind of made it much more difficult to have a conversation, because I didn't know who this person was. And it was kind of like, okay, what, and that's right. I think people said a little bit about what they did, and they just sort of said, I'm John Smith. And that was it. I think that may have been the first time I actually met John McCarthy in person. John Smith was John McCarthy, needless to say. So a bit prickly. I think I had all kinds of subsequent interactions with John McCarthy. I think when I first started working on cellular automata and on simple programs that can do complicated things, I I must have been having sort of a continuing interactions with John McCarthy at that time. That was probably 1983-ish. Anyway, I sent John McCarthy a copy of this really short paper, like 3-page paper that I'd written about this stuff, summarizing what was going on. And he sent me back this, I don't know how long it was, 8-page typed letter about why my 3-page paper was nonsense. And it was not a particularly well-reasoned piece, but it was basically, look, we know a Turing machine can in principle do anything. So why is it news that a simple cellular automaton program can do complicated things? Well, the reason it's news is because we knew that in principle a sufficiently complicated Turing machine could do anything you want with sufficiently complicated programming. The news was that a very simple program, a kind of Turing machine that you might pick at random, or a cellular automaton that you might pick at random with a very simple initial condition, with very simple programming, would do something complicated. That was news. And John McCarthy he didn't think that was interesting. I don't remember. Someday I'm going to put a lot of these archival materials that I have on the web. There's a lot of interesting letters from lots of people, but that's and I haven't looked at that letter in decades probably. So I can't tell you in tremendous detail what it contained. But I remember, I don't really know, the personal history of John McCarthy. I think he had been at MIT, then he was at Dartmouth. Then he went to Stanford pretty early in the history of the Stanford Computer Science Department. I think he'd had some sort of personal misfortunes and things, which people say made him a bit more prickly than he had been previously. But I think certainly my interactions with him, certainly I remember my New Kind of Science book. I had a variety of interactions with John McCarthy, it was with a definite flavor from my side of, why don't you actually read what it says, rather than thinking that you know what it says, because I don't think you know what it says, because it's actually surprising. But anyway, and I think, but that was, I have to say, I was very impressed. I looked again recently at John McCarthy's 1959 paper about Lisp. The thing that, and it's a very good, clean paper. Anyway, a little bit more about Lisp. I can tell you a few more stories about Lisp. Back in the beginning of the 1980s, people were very keen to see, could we really make Lisp run fast? And so one of the things that happened was that there were, people said, well, let's just implement Lisp in hardware. And so there were 2 companies that spun out of MIT. MIT was sort of the big Lisp place, and along with Stanford, I guess. But MIT somehow had more energy around this. And so there were 2 companies that were started at that time. One company called Lisp Machines Incorporated, LMI, and one company called Symbolics. And these both had some kind of license to various technology from the MIT Lab for Computer Science or maybe the AI lab, I think more likely the AI lab, to go and build these hardware Lisp machines. Actually, that was it was a time when sort of the early days of kind of sort of the interaction between, is software a thing that gets paid for by people who use it, or is software a thing that gets paid for some other way, and how that all worked. And I know Richard Stallman was a person who was around at the AI lab and working on things like emacs and so on. And I think that the thing that was that one of the things that happened was, as these companies were getting formed, it was kind of the schism of where people were going to go to this company and they thought they might get rich, and going to go to this company, and Richard Stallman was kind of left out of the whole thing, and he was all upset. And I think that was a part of the motivation for the whole, free software, let's just these companies be damned type thing. But in any case, as it turned out, symbolics eventually went public, I think. Yeah, I remember that. And there were a bunch of people who were sort of the early Lisp hackers who, all had a little bit of stock in symbolics and did well from it. I think I actually just recently, just a few days ago, I happened to be giving a talk at MIT, and I was, for quite different reasons, looking for something else, and chanced upon this stuff about MIT and found this actually a printout of me logging into the MIT MC computer system in 1980 through the what was then the ARPANET, now the internet. And it was kind of fun because there was a little bit of email that was there, and I need to send that to a friend of mine with whom I was having an email correspondence at that time, and point out that we really were early adopters of email back in 1980, and actually all the way back to 1976 or so. But in any case, I found, along with that, an interesting piece of email that I exchanged with a person called Joel Moses, who had been I don't know if he's still around, but was a longtime MIT person, became a sort of senior administrator, I think, at MIT, but had been much involved with the creation of this thing called Maxima, which was a Lisp-based mathematical computation system. But in any case, this piece of mail was about what would happen to Maxima, and was it going to be a kind of free system? No, Joel Moses said, no, we're going to charge at least $10,000 a year to people who want to use it, and so on. So it was sort of interesting to see that as a thing emerging at that time. Well, anyway, the Lisp machine companies came, and actually they built some very nice stuff. I didn't ever use their technology very much, but it was an interesting kind of approach where sort of the whole operating system was written in Lisp. It's kind of thing that would be like writing sort of everything like I try to exist mostly in Wolfram language today. It's sort of the same story as the Lisp machines existing, sort of Lisp all the way down, so to speak. But one of the things that sort of happened to Lisp was the things like Common Lisp, which became a very, very, very complicated system, and it kind of didn't. In what we've done with Wolfram language, there's kind of been a sort of an approach to kind of dealing with sort of the complexity of the language and the scope, and thinking about it as a language to describe the world. Whereas I think Common Lisp just became more complicated as a pure programming language, and people would probably say that it had become way too complicated and possibly unimplementably complicated. But that was sort of a bit of the story of Lisp. Let's see. Okay, let me look at a few. Oh boy, all kinds of. There's a question: how is emacs related to Lisp? Well, it uses an underlying kind of Lisp-like. It has a Lisp as its sort of underlying. It's very, very advanced, really. Emacs was a Richard Stallman production. I mean, I should say, I think this is no longer a secret, but long ago, there's that outfit called the MacArthur Foundation, who were kind enough to give me one of their sort of, they used to be called prize fellowships, I think, but one of their, fellowships back when they were first giving these things out in 1981. And so they would always ask, oh, can you suggest other people who should get these things? And one of the people I suggested long time ago was Richard Stallman, thinking about the kind of the GNU C compiler and Emacs and so on and so on and so on. It was kind of interesting for me because yep, he got this thing, and which I thought was great. And then subsequently he really got very big on the whole free software thing. And I would meet him and he would be like, this stuff you're doing is terrible. You should be giving everything away, and that's the only way to make progress, and so on. And I have to say, I said to him at that time, I'm not sure how it's going to end with you saying you're just going to give everything away. I'm not sure that's really going to work out. I don't think that's a sustainable model that will lead to sort of happiness of everybody. And in more recent years, I run into him and I say, so what happened with Linux? And he's like, oh, that's so terrible. They took GNU, they took everything I'd done. And I was like, but didn't you say it was free for the taking and so on? And he's like, yes, but not in that way, et cetera, et cetera, et cetera, et cetera, et cetera. So it's one of these, a little bit, for me, it's one of these, a little bit, I told you so. But actually, a few years ago now, the thing I told you about suggesting him is definitely not a secret, because I happened to be at some event where the person who's now running that program, and I was talking to that person, and Richard Stallman walks up, and I somehow this came up, and I just explained this piece of history right then, right there. So, and that's the first Richard Stallman had heard of it, and so I think it's now an out in the open kind of fact. But it's kind of it's one of those interesting dynamics of the people don't necessarily like you or hate you for the right reasons, so to speak. In any case, let's see. It was a question about, it's a question from Colin Fields. Do I know Linus Torvalds? I do not know Linus Torvalds. I know a lot of people in the software industry. I do not personally know Linus. Let's see. Questions here. Oh my gosh, so many questions. Let me just talk about ones that are somehow related to what I was just talking about. Okay, there's some questions from Mikhail here. There's a comment that on Lex Fridman's podcast, someone was talking about Joshua Lederberg in the 1960s using AI ideas to help NASA identify molecules related to alien life. I suspect that was part of the whole sort of Dendrel story of identifying and this kind of idea of chemistry as theorem proving and so on, which is something which I think is it's time to bring that back. Let's see. Questions here about okay. There's a comment here that from Parmenides that NASA became interested in Sanskrit as a programming language. I did not know that. That's cute. Okay. Well, let's see. Oh gosh, so many questions here. There's a question from Mikhail about what are the contributions of Marvin Minsky to AI? I knew Marvin pretty well for many years, actually. I even wrote something about him when he died. So if you're interested in more details that I perhaps won't remember right now, I refer you to that. It's also in this book called Idea Makers that I put out about historical biography. Well, Marvin. So, I mean, Marvin was sort of, he had wanted to study neural nets from an early stage, but he kind of got into doing, he did his PhD at Princeton in fairly traditional math. I think he had wanted to do kind of neural net math, but nobody had let him do that. And so, and he even started building, hardware neural netty type things in the 1950s, trying to explore these kinds of things. He ended up, one of his contributions to the neural net field was this book that he wrote with Seymour Papert. Seymour Papert is particularly well known as being the creator of the Logo programming language. Yes, I also knew Seymour Papert, though not as well as I knew Marvin. But anyway, they wrote this book called Perceptrons, which kind of killed perceptrons, and it kind of killed neural networks, actually, because what they did was they showed that, in a sense, perceptrons that had been invented by this guy Frank Rosenblatt were sort of a one-layer neural net in modern terms. That these perceptrons could be represented in quite simple mathematical terms. They're sort of just finding nearest neighbors in this kind of linear way. And so, in a sense, that book showed a one-level neural network couldn't do anything interesting. It was just doing the simple mathematical operation. Well, as is so often the case, people ignored the little footnote that said one-level neural nets. And for many years, it was like, neural nets can't do anything interesting. Marvin and Seymour proved that neural nets can't do anything interesting. And it was not until the 1980-ish timeframe, the whole sort of parallel distributed programming, and like my friend Terry Sinofsky and people like Jeff Hinton and other people sort of brought back the idea of neural nets and said, well, actually these multi-level neural nets, which have been much more difficult to train, perceptrons are rather easy to train, we should really look at these, and these might be interesting. But that was, and at that time, they still didn't really get started. The whole sort of deep learning, deep neural net type thing didn't really get started until around 2011. But it had been sort of slowly smoldering from the 1980s on, having been originated way back in 1943 by McCulloch and Pitts. But so one of Marvin's contributions, which he always was rather unhappy about, that this had been its, well, at least subsequently he was unhappy about it. He didn't really, I mean, he was around in the sort of the rebirth of the neural net, interest in neural nets, but he didn't really engage in that, I think. I'm trying to remember if I ever talked to him about that. I'm sure I must have done, but I don't think he really engaged at that time. But, he was very much involved in kind of the, having done the neural net thing and having written the perceptrons book and having sort of, this kind of statistical AI machine learning thing isn't going to work. Let's do more symbolic AI. Let's do more kind of AI that is based on kind of reasoning and sort of logic and things like this. And he then had a sort of a series of models for kind of sort of a mixture of how the brain works and how AI might work, and the theory of frames and a whole bunch of theories, which I have to admit I'm not completely sure I ever completely understood. Some of those theories led to spin-offs like the whole connection machine computer thing. His student Danny Hillis ended up sort of, let's make this in hardware. And that became a sort of a massively parallel computer, which I can tell you many, many stories about. That will be a separate topic. But that was another kind of a spin-off of sort of Marvin's theory of mind type thing, sort of computational, a possible computational theory of mind. I must tell a personal story perhaps about Marvin. And this is where, I still have to define my rules for these historical discussions. But Marvin's daughter, Margaret, is somebody I've known for many, many years. This must have been 1984 or 1985. Margaret was spending the summer in Japan. I was living in Princeton at the time, and I was going to spend part of the summer in Boston. And so I sublet Margaret's apartment from Margaret for a couple of months or whatever it was. Okay, so there's Margaret's apartment, and one of the features it had was a very large number of plants, there's a whole sort of I don't know, almost greenhouse full of plants there. It wasn't quite a greenhouse, but it was sort of a side part of the whole thing was this thing with all these plants. And so I'm like, okay, I try and water your plants. Do they really need, what am I supposed to do with your plants? Okay, well, you could water them. But anyway, so I'm doing this, and I see these plants have little white spots on them. Their leaves have little white spots on them. So it's like, what am I going to do about Margaret's plants, which are clearly have some problem, but I'm not not enough of the web didn't exist. I couldn't go look up white spots on this kind of plant. What am I going to do? So, and Margaret was off in Japan and et cetera. So I call Marvin and I say, so Marvin, Margaret's plants have white spots on their leaves. What should I do? Marvin launches into this long, probably hour-long discussion about micro robots and the idea of, we really should have these things that are like, flying micro robots that would go and attack the little parasites that are attacking the plants and so on. It was a lovely conversation about sort of the future of micro robots and so on. And at the end of this whole long discussion, I'm like, okay, Marvin, but what should I actually do about Margaret's plants? And he said, well, you should talk to my wife, Gloria. And so she had some practical thing to say, which I don't remember, but that was a very typical Marvin interaction. I mean, I'm now remembering, I think probably the first time I met Marvin must have been 1978, 9, something like that. Marvin came to visit Dick Feynman, who I knew quite well at that time. I was at Caltech. He was at Caltech. We were trying to do some work together. Must have been, oh gosh, well, probably 1980. I would guess this happened. So anyway, so Marvin. What was the whole detail of this? The thing that sticks in my mind is we're driving through Pasadena, Marvin, Dick Feynman, myself, and I kind of think Marvin was driving, and I kind of think that Marvin was launching into this long description about autonomous driving and self-driving cars and what will be involved in doing them, and look at how complex it is to figure out, the rules for what to do at this intersection, that intersection. And I have this recollection. This is a very long time. I haven't thought about it. I think I might have written about this in the piece I wrote about Marvin. I have this recollection of being really a bit terrified by the actual driving that was going on, with this whole discussion of but AIs will be able to drive real soon now. That was 1980. I think we're still far away from self-driving cars that can deal with the complexities, even that we were seeing in some of the situations there. But anyway, so Marvin was very much of a thinker far into the future about all these kinds of things. I think that in terms of his actual concrete models about AI and so on, I'm not sure what to say about that, because I remember he wrote a book called Society of Mind, and he gave me a copy of this book before it came out. It must have been mid-1980s, and it was originally he was going to write that book in poetry. I think many people, I was certainly one of them, said that's really a crazy idea. But as it was kind of a one idea per page book. And these ideas range from really quite interesting and thought-provoking to like, whatever type ideas. And I think Marvin then wrote a book, I think it was called The Emotion Machine, which he spent a lot of effort on. And I talked to him about that at some length. And I tried to say sort of, what kind of a thing is this? Are you kind of channeling something like Freud, who had sort of a theory of the mind and its operation? Or are you channeling something that is more like sort of a more mechanistic or more sort of operationalizable sort of AI kind of thing? And I think it was kind of interesting to hear that that sort of discussion of, and I think he thought it was more like kind of a Freud type story of this was a kind of explanatory framework for thinking about emotions and so on. And Marvin was big on these kind of theories of, I don't know, he was like, what is the cause of humor type thing? Why do people laugh? How does that, what is the mechanistic, almost Darwin-like, Freud-like form of explanation of what was going on? Now, that was sort of the later years of Marvin. In the earlier years of Marvin, before I knew him, in the 1960s and so on, one of the things he did, he wrote a book called Computation, Finite and Infinite Machines. It's a great book. It was one of the first sort of clear descriptions of, Turing machines, tag systems, this, that, and the other. It didn't mention combinators. It didn't mention some of my other favorite systems. Didn't mention cellular automata. But it was a system. It was a book that kind of really set down in a clear way sort of some of these early models of computation and how they were related and so on. And I think partly in connection with that book, Marvin tried to find what was the simplest universal Turing machine. And he found this Turing machine with 4 colors on its tape and seven head states. And that he found that in maybe 1962 or so, partly in connection with this book. And he also told me he had studied the Turing machines with 2 head states and 2 colors on their tape. There are 4,096 of those. And he'd looked at them. And in fact, I think he says in the book that you can examine their behavior, but you wouldn't want to. It's too tedious and so on. And I have to say, it's kind of funny because just in the last few days, I've been looking at things related to Turing machines, and those I've been, nowadays it's just an instant, in Wolfram language, there's a function called Turing machine, and it literally, you just, boom, you can get the behavior of all those 4,096 Turing machines, and you can verify what Marvin also discovered around 1960 or so, that yes, none of them can do anything terribly interesting, and none of them can be universal. But Marvin at that point sort of said, well, it's too complicated to find, to try and explore what Turing machines do by any kind of experimental means. And then he found by sort of theoretical work, this 4-7 Turing machine that was universal. Well, for many, many, many years, that was the simplest universal Turing machine. Actually, until, well, I kind of found a Turing machine in the mid-1990s that I guessed might be universal, that had has 2 head states and 3 colors on its tape. I didn't know whether it was universal. We put up this prize. It was, what was it? $25,000 prize we put up in 2007 for somebody who could prove or disprove that this Turing machine is universal. And a young chap, was a then young chap named Alex Smith in England, who was at that time a student studying computers into kind of exotic programming languages and so on. I think as now works on compilers and so on. Anyway, he proved that Turing machine is actually universal, and I think Marvin was a bit disappointed when his record for the 4-7 Turing machine was finally broken after, I can't do the math, after whatever it was, nearly 50 years or something, by what is now we now know as the minimal universal Turing machine. Marvin was on the kind of I got him to be on our prize committee to kind of assess potential solutions to this project. So he was aware of that. But I thought, Marvin's early work on sort of theory of computation was really very strong and very, very sort of clear. His work on sort of AI and these kind of models of AI, it became a little bit unclear kind of what the point was, what kind of a thing was being deduced. And as I say, I think it should more be thought of in a kind of Darwin, Freud type way than in the way that one really thinks usually as of sort of computational science, mathematical science operating. But Marvin was always, I don't know, he was very big on the let's try and think about things in a different way, even if it's kind of weird. Like I remember one time, not so many years before he died, I was at his house and he says to me, what would you conclude if the sun didn't come up tomorrow? And it's like, well, Marvin, let's take apart that question. And, what kind of a thing do we mean by that? And, would we conclude there was some bizarre atmospheric phenomenon that was, blocking out the sun, or do we conclude that the earth had stopped and so on? But it was a funny kind of question, a funny kind of construction. But Marvin liked those kinds of things. And I think Marvin was also very much into all of these kind of thought experiment type questions. And for example, he was interested in physics. He never really, I think, knew that much about sort of the 20th century developments in physics of, quantum field theory and general relativity and things like that. But he was interested in physics. And, there was a time in the 1960s when it just looked like, the computing paradigm, what we now believe actually, that the computing paradigm is just going to solve everything. But it looked like that was really close at hand. And so Marvin and others were like, well, maybe we can solve physics too. And I think he wrote a little paper called Nature Abhors a Vacuum that was about kind of, there must be, photons must be, it's kind of like the ether that people have believed back in the time of Maxwell and so on for the the luminiferous ether in which light waves will be carried as sound waves are carried in air type thing. And Marvin was like, but computation must let that be something that, if we think about the world computationally, there must be similar kinds of things going on. And there was a certain amount of weirdness with, maybe Marvin wasn't perhaps involved with this, but my friend Ed Fredkin is always bringing this story up as an example of how people don't understand things. That people were saying, well, look, if the universe is computational, what about the round-off error? Because after all, we know that, physics involves numbers and numbers with certain precision. And what about, can't we detect the round-off error? Well, at some level, that's a correct thing to ask. Can't we see the granularity of space-time, for example, if space-time is granular? But it's not really the right thing to talk about it as round-off error. That's really a different kind of concept that comes once you have numbers and computers and you're sort of casting those numbers into digital form. But yeah, I could probably tell you a lot more things about Marvin. I think that for me, sometimes Marvin was a little frustrating. I mean, I always enjoyed him because he was always a person who would just have the wildest things to say. And he had this house in Brookline, and just across the river from Cambridge, it was a house full of just the most amazing stuff. And I think, unfortunately, particularly his wife was involved, just collected an awful lot of stuff to the point where there was this terrible disaster when a ceiling finally collapsed. And now the house is quite cleared up. That stuff included things like, the early Apple stock certificates that were found, stuffed somewhere. That I think I have that right. It might be a different company, but I think that's but just a wonderfully eccentric kind of setup. Anyway, let's see. The questions here about from Juan about scheme. Well, scheme was really the Jerry Sussman, who was a student of Marvin's, was, I think, the main person behind scheme, which is sort of a derivative of Lisp. I don't know much about it. I mean, I know Jerry Sussman, though not I haven't seen him in years, actually. Yeah, I really have little to say about that, unfortunately. I mean, Jerry Sussman went on, in addition to doing scheme, did some interesting projects like this kind of digital orrery, trying to compute the motions of planets for long periods of time to find out about stability of the solar system, all sorts of fun things like that. Let's see. All right, let's address something different here. Okay, there's a funky question here from Mikhail. Why did Ludwig Boltzmann commit suicide? Well, that's always, unfortunately, that's always more of an internal psychological question than anything else. But I'll tell you the kind of the folk story, and I'll tell you what I know about the real story. So first thing, Ludwig Boltzmann was a German physicist in the mid to later 1800s. And he was most famous for introducing the concept of entropy as a counting of state, for relating entropy to the counting of microscopic states and things like gases. And that's what led to Boltzmann's constant, lowercase k. That's the constant of proportionality between temperature and energy. For degrees of freedom, like motions of gases, motions of molecules and gases, and so on. But Boltzmann was really an early person in the development of statistical mechanics. And one of the things that is often said, kind of the folk story, is that Boltzmann never managed to convince people about his work on statistical mechanics, and that made him depressed, and so he committed suicide. I think the truth is more complicated. I think he had some nasty medical condition that really impacted his quality of life, and I think he was that was probably another big factor. I found it fun to realize that the way the times line up, the late Boltzmann was the early University of California in Berkeley. And the late Boltzmann, with all these pictures you see of him with a big bushy beard, looking like the quintessential kind of 1800s German professor, actually he spent some time in California, the place that hadn't had a gold rush too much earlier, at the new University of California in Berkeley. And I kind of wonder what that was like at that time and what his interaction. I kind of have this image of him as the quintessential kind of classic, kind of stiff German, professor of the 1800s. And so I kind of wonder what that was like in the, going to the Wild West, so to speak, of the late 1800s at UC Berkeley. I don't really know. But in any case, the big thing that Boltzmann, Boltzmann had this idea that entropy, which was a thing that had been observed that had been used by people thinking about things like heat engines and questions in chemistry, was sort of a property of materials that you could attribute a certain entropy to them that was different from their energy. It was another kind of quality. And what Boltzmann said was that you could associate entropy as being sort of a counting of the number of microscopic possible states of molecules consistent with the macroscopic observations of the material. Now, of course, at that time, molecules were kind of a new thing. I mean, it was only 1840s, 1850s, people discovered, when was Brownian motion? Maybe 1830s, 1840s. Brownian motion was one thing, and then there was the Dalton's work a little bit earlier than that on kind of the numbers that occurred in chemistry and how, there were 2 of this and 3 of that, and you could account for sort of chemical reactions that way. And that kind of gave this indication that there were really discrete atom-like things. But atoms, people didn't really know that matter was made of atoms. And that was sort of a somewhat new thing in Boltzmann's time. And I think that so that was to think about, what was the macroscopic consequence of the fact that things were made of atoms was an interesting thing. I think one piece of history that I do recall is this strange kind of chain of history in which, in a sense, Boltzmann thought about his. I think there's dates. There's some date markers here. So 1859 was the publication. Assuming I don't get these dates wrong, dates from memory are always a little bit scary, but was the publication of Darwin's Origin of Species. And one of the things was that Boltzmann actually thought about his sort of evolution of molecules, evolution of the configurations of molecules as being something that he was sort of deriving in some sense from, not in a mathematical sense, but in a conceptual sense, from kind of Darwin's, there are all these little individual organisms and they're struggling for life and so on. And they have some aggregate effect that might be the whole development of life on Earth. And I find it kind of interesting because Darwin, on the other hand, was somewhat channeling Malthus, who had been talking about kind of economic kinds of questions. In his sort of struggle for life, he was kind of channeling, Malthus's ideas about, how economic systems work. And so it's kind of a funny chain because it went, in a sense, the flow of ideas went from economics to biology to physics, which is kind of the exact opposite of the way that one might think in more modern times that things should flow. So I think it's sort of interesting that was the way the intuition went. But anyway, Boltzmann, one of the things that he wanted to show was the second law of thermodynamics that was kind of a thing of the 1860s or so, that people had observed this entropy tends to increase, and people like Kelvin had been in that picture. Who was the, oh my gosh, Rumford, is that right? Am I remembering correctly? People, I think Carnot might have been, and Sadi Carnot might have been involved in that also. The sort of the realization that, yeah, in fact, Carnot must have been involved because one statement of the second law of thermodynamics says heat doesn't spontaneously flow from a hotter body to a colder body. And that relates much to kind of Carnot's sort of engineering style heat engine treatment of thermodynamics. But anyway, so there was a question of why is it the case that heat doesn't flow from a hotter body to a colder body? Why is it the case that things, mechanical motion degrades into heat? Things tend to end up going to this situation where there's heat and not systematic mechanical work. This was a story of the increase of entropy. And that was the thing that Boltzmann set out to explain from his microscopic theory of molecules. Well, so he made up this thing called the Boltzmann equation, still used today, which is an equation that describes, with differential equations, describes the microscopic collisions between molecules and the consequences of collisions between molecules, and describes the kind of distribution of molecules that you get from a sequence of collisions between them. And so what he then came up with this Boltzmann equation, and from that he proved this thing called Boltzmann's H theorem. And Boltzmann's H theorem basically says that this quantity called H, which is now actually, I think it's minus the quantity we now call entropy S, that basically the upshot is this theorem claimed to prove that entropy increases with time. Okay, the problem is that underlying that is a model for molecules bouncing around that is completely reversible in time. So just as you can run Boltzmann's H theorem and say entropy increases in time, so you can also run it and say entropy decreases in time. And people pointed this out. It was called the reversibility objection. I think Loschmidt was responsible for pointing that out, if I'm not mistaken. But people were like, Professor Boltzmann, this cannot possibly be correct. It goes the other way, et cetera, et cetera, et cetera. And I don't know if Boltzmann ever really understood what was going on there. And I think people, would say, so your whole theory of entropy coming from microscopic molecules can't be right, et cetera, et cetera, et cetera. And people didn't really believe it. In the end, the real issue is that what he was assuming is the so-called molecular chaos assumption that molecules are uncorrelated before they collide, but after they collide, they get correlations. And so when you run things backwards, you have to say, well, they're uncorrelated in future, and then rather than they're uncorrelated in the past. And that's sort of why you break out of that idea. So I think the thing that, so anyway, I think Boltzmann kind of sadly went to his grave not really understanding sort of the resolution of questions like that. And famously, his tombstone has, I think it says S equals K log omega, but that doesn't jive with the fact that there's an H that he defines. So maybe it was called S by that time. But anyway, that was his story, is this relationship between entropy and this microscopic character of things. I mean, that relationship, that idea of statistical mechanics, this idea that you can kind of get aggregate properties of things from the sort of the aggregate of lots of discrete molecules bouncing around. James Clerk Maxwell famously derived the Maxwell distribution of velocities and gases. That was a thing that he did. He did that actually as part of a kind of a school assignment. Well, kind of. I think he was competing for some essay competition that was supposed to be about the moon, the rings of Saturn. And so somehow the young Jamie Maxwell thought, look, I'm doing this exercise about the rings of Saturn, but I've got to do some more basic science to figure that out. And then he figured out the Maxwell-Boltzmann distribution of distribution of velocities of molecules in a gas. And then subsequently, by 1900 or so, I actually only recently learned this. People like David Hilbert, who was sort of a big figure in pure mathematics, was very, very, very interested in this whole question of statistical mechanics, this question of how microscopic atomic processes could become this macroscopic phenomenon of things like the flow of fluids, continuous flow of fluids, and so on. I find it interesting. He spent about 20 years working on that before coming back to working on foundations of mathematics and so on. And he didn't really solve those problems. Turns out those problems are really front and center in the work we're doing on fundamental theory of physics now. And the problem he was trying to solve of could you understand things like space as discrete and with some kind of continuum limit, that's the exact story of what we're trying to solve now. It's a shame that David Hilbert didn't have the sort of computational paradigm we have today. I mean, strangely, as I sort of really studied last month in connection with the centenary of Moses Schoenfinkel and the invention of combinators, David Hilbert had computation right under his nose. He went to the talk almost certainly on December 7th, 1920, in which Moses Schoenfinkel introduced combinators, which were the first sort of really concrete formal version of computation as we know it today. But all those connections weren't made, as usually these things aren't. And it took another many, many, many decades before that really became clear. But then in statistical mechanics, the next big figure was Josiah Willard Gibbs, who was an early American physicist, worked at Yale. he was the person who, must have been 1910s, 1920s, things like that, was really a person who sort of put more serious mathematical structure into thinking about thermodynamics and things like Gibbs ensembles and the Gibbs rule and all these other kinds of things. And he really tried to sort of put the math into thermodynamics. Anyway, let's see. Okay. Fact check here. Just Boltzmann's tombstone says S equals K log W. Okay, so the W got capital W. So I think subsequently it was a capital omega was used for that. Okay, there's so many interesting questions here. I'm sorry, I'm having a hard time. And by the way, feel free to ask about more detailed questions about people. And you know, I've had the good fortune over the last probably 50 years to meet, almost 50 years. I've been sort of somehow doing sciencey kinds of things, to meet a good cross section of kind of people who've been doing science that impinges on kinds of things I've been interested in, at least. And I certainly can try and give you my impressions of some of these people that might be of interest. Well, there's a question from Parmenides. If you had to choose only one country's mathematics that you would be allowed to use, which one would it be? England, France, or Germany? Oh boy, I mean, the traditions of mathematics in past centuries between different countries are very well, were sort of different, although, you know, it's funny because, for example, the modern notation of mathematics is completely international. You know, you don't see, I mean, people write, you know, it's very rare that the pure notation is sort of international. Now, sometimes in like Russian papers and things, you'll see something like determinant for debt. You might see a different word for that little fragment there. And you know, the origination of the international version of mathematical notation was in a sense by design. I mean, people like Gottfried Leibniz in the late 1600s, who was inventing some of this notation, you know, the d by d whatever, the integral sign, all those kinds of things were Leibniz's inventions. He was, you know, his day job was sort of being a diplomat type, or at least a backroom, you know, study the facts diplomat kind of person. A staffer, I suppose one might say in modern times, although I think he did do some frontline diplomacy, but he was more like a courtier staffer type person. But anyway, he really wanted to use mathematical notation as a way to have an internationalized way of communicating mathematical ideas. I mean, I think he was living at a time when Latin, which had been for 1,500 years, or at least 1,000 years, kind of the language of scholarship, the language of learning, was beginning to sort of break up into people were using English, they were using German, they were using French as sort of the language of scholarship as an alternative. And so, you know, he was sort of hoping that by having, and it was successful, by having this mathematical notation, he could have this kind of international standard for how mathematics would be described. But I think the actual traditions of these different countries ended up being a bit different. I mean, you know, for example, in calculus, there was kind of the continental tradition that followed Leibniz and the British tradition that followed Newton. And Newton had a very geometrical view of calculus. Leibniz has a very sort of algebraic view of calculus. Newton had this whole notion of fluxions and you know, x dot and so on. That was the whole Newton notation. I would say that Newton was not as notationally sophisticated as Leibniz, didn't really pay so much attention to notation. He was much more, you know, doing things in the style of Euclid, proving sort of geometrical style proofs and so on. I remember Newton had various kinds of names for things, like kineton, I think, was one of his names. I'm trying to remember. I remember when I was a kid, I grew up in Oxford, England, and there was a road called Kineton Road. And again, it's a pity the web didn't exist, because I would have just typed it in and I would have known all the story, and I'm sure one can immediately do that. But I'd said, what on earth was this thing? That's not a standard road name. And it was apparently some kind of Newton spin-off type thing, although Newton was primarily a Cambridge man. I think so I mean these kind of the different traditions of different countries. What happened in France, for example, in the 1800s, there was this much more kind of formal, structured tradition as well. That was really much more abstract, and much more, a move towards abstraction, a move towards sort of precision and abstraction. The British tradition was much more of a let's just hack it together and make the math work and learn a bunch of tricks to, was a lot of, the Cambridge Wrangler, mathematical Wrangler, let's learn all these clever ways to do integrals and all these tricks for doing integrals, rather than let's find the sort of abstract characterization of what's going on in integrals. And people like, Babbage famously was like, let's reform the way that Cambridge mathematics works. Let's bring in some of this more abstract continental stuff. I would say that the German tradition, if I were to characterize it, might have been a little bit more. I would say the French tradition was, definitely had a more geometrical flavor. The German tradition had a more algebraic flavor. People like Grassmann and so on were very much into the sort of the formalization of algebra. Whereas the sort of, I would say, I mean, there have been people like Galois in France, but I would say that in general, there was a little bit more of a geometrical flavor to sort of the French tradition. And that led eventually to people like Poincaré, which was sort of a somewhat more geometrical take on how things worked, and the invention of topology and so on. But I think that it's also worth realizing as we look at the history of those times that there were things like the three-body problem, the gravitational the problem of gravity between the Earth, Moon, and Sun. That was a big dominant problem of the 1800s. That was the holy grail of a lot of that mathematics, and a lot of things were done, including even the invention of topology, was done sort of in the service of that kind of idea. I think it's, in more sort of supporting this more algebraic style of things. People like Cantor were working in Germany, inventing transfinite numbers towards the end of the 1800s. People like Frege inventing kind of this sort of math is built on logic, more sort of algebraic tradition stuff. I noticed that Parmenides mentions Russian mathematics, which certainly became significant in the 20th century. I'm the pre-20th century Russian mathematics. I'm familiar only with some small pieces like Lobachevsky and so on. I have the impression that really developed in the particularly in the 20th century, but I might be wrong about that. I'm not sure. I suppose the people like Euler, who was kind of, that's a complicated case because Euler was hanging out in Königsberg, which was in Prussia, which is sort of Poland-ish type area, but he was also, Swiss, Prussian, Russian. He also spent time in the Russian court, so that may have been a sort of Euler famously has this book. What's it called? Letters to a Russian princess, right? I think that's its name. Yeah, which was so he was sort of involved with those kinds of things. Let's see. Oh boy. This is there's a question from Lexibit about visual programming languages. I think that's probably not for this live stream. Let me talk about that in a different place. There are questions here about people. Did I interact with Jim Watson or Francis Crick? Yes, some good friends of mine were good friends of Francis Crick's, and I ran into him quite a lot of times. Jim Watson I run into only a few times. I would say Francis Crick, was always, I think, the let me have a crazy idea kind of guy. When I knew him, he was really into kind of brains. He was at the Salk Institute at that time in San Diego, and he was really into kind of things about brains, and he had sort of theories of sleep and so on. And he was coming up with all these crazy theories. Once upon a time in 1953, he had a crazy theory that maybe, the DNA molecule was storing digital information about genetics. That crazy theory turned out to be right. I think I'm not sure that any subsequent Francis Crick theory turned out to be right. They were interesting, not necessarily right. He had theories about consciousness and a lot of theories about how brains work. I mean, Jim Watson, I think, was always very, in the times I interacted with him, quite a dogmatic fellow about, with a very much I would say, in some ways, a scientist with a definite view of kind of, here's how science should work, and everybody who isn't a scientist doesn't know what's going on, which I think sometimes led him astray, and particularly in areas of public policy and so on. And I remember one, I remember a weird interaction with Jim Watson about some, science versus religion discussion, which made me not, kind of made me feel that it's like, I think you're just being dogmatic. It's not, you're not actually thinking about the real issues. It's more just, this is science as scientists think it should be, and sort of following that that idea. I think I should wrap up soon here, but there are questions. I'm being corrected on the Euler. I thought that didn't sound right. Euler's book was Letters to a German Princess, not Russian. So I was wrong there. I thought it didn't sound right. Oh gosh, there are questions here. I'll do a few of these and then we should wrap up for today. There's a question from Solo about, do you apply Monte Carlo simulation in any of my work? Sometimes I sample things at random. Usually I prefer to have a system make its own randomness. I have to say, I did know Nick Metropolis, I guess the inventor of the Metropolis method for doing Monte Carlo sampling and so on. He worked at Los Alamos. He'd been one of the people who worked on the Manhattan Project, and some group of people from the Manhattan Project kind of stayed on at Los Alamos. Stan Ulam was one of them. Nick Metropolis was another, I knew these people in the early 1980s when I spent some time at Los Alamos National Lab. Let's see, there's a question here from Ezekiel. Did I ever meet Konrad Zuze or study his work? Okay, I will tell you a little bit of, there's a comment here from Caparn saying, I ran into Aaron Klug and Max Perutz. Max Perutz was lovely. Aaron Klug just told me, cleaner, get out. Okay, he used to clean their offices. Interesting, okay. I ran into Max Perutz somewhere, and I also thought he was a lovely fellow. But about that, I think he was involved with the Cambridge, the whole Cambridge crystallography crowd. And I guess I ran into some of those people, if I'm not mistaken, when I was a kid. I was a pretty young kid, like 11 maybe, right? 11, 12 years old, something like that. I went to stay with a friend of my parents who was an academic in Cambridge, and I went to somehow I was, a science kid, so it's like, come and see the cool science things in Cambridge. And so two cool science things I saw. One was at the Department of Crystallography, which existed in Cambridge at that time. I think it was probably a spin-off of the Bragg father and son team who'd invented X-ray crystallography. But the cool thing for kids at that time was they had a piece of moon rock. And so you could kind of see and they also had a scanning, an electron microscope. And I even have somewhere, somebody there gave me, as a science kid, they gave me this photograph that had come out of their electron microscope of their piece of moon rock, which I'm sure I still have the photograph from the microscope at that time. But there were a bunch of crystallographers. Duncan McKee, I think, was one of them, and a few others who I, as a pretty little kid, ran into. And another site I remember seeing in the Cambridge, tourist, the Cambridge, 11, 12-year-old, whatever. I think I must have been 11 at that time. Yeah, sounds about right. What does the 11-year-old science kid see around Cambridge? The other thing to go see was the radio telescope. And now maybe it was earlier than that. I'm forgetting. Maybe it was 2 different trips. But anyway, I see this radio telescope, and it was a kind of, I guess, what would now be called a synthetic aperture telescope. It was instead of being a big dish like Jodrell Bank had been, it was this thing with just a bunch of separate antennas out in this field, I think in Madingley Road, Cambridge, if I remember correctly. Anyway, we go out there, and there's this little hut where there's this kind of place where there was the kind of oscilloscopes and things, and the whole sort of control thing. And met a chap there called Tony Hewish, who was one of the, as it turns out, one of the creators of that radio telescope. And someplace I have some, I think it was a thing I'm not sure I did much of. I did a lot less of it than I should have done. Was getting. Well, no, maybe I didn't get a signature. I think I just have a diagram, some diagrams that he drew for me about how this telescope worked and so on. And that telescope, of course, was the telescope that had discovered pulsars in 1968. And I'm kind of thinking this was like 1969 or 1970, because it was very soon after the discovery of pulsars. But these things weren't famous then. And Tony Hewish went on to win a Nobel Prize and all this kind of stuff. But that was just the who do you run into as a kid? I mean, I remember there were all kinds of strange scientists that I ran into in the kind of Oxford Cambridge circuit as a kid, and I certainly developed an impression of, although probably not a very deep one at the ages I was then. I think. Anyway, the thing that I'm kind of inclined to start talking about another scientist from those we're going to come back to Konrad Zuze in a moment, and then we should probably wrap up. But a scientist of that time who I got to know quite well in later years was Sidney Brenner. Sidney Brenner is sort of in the news now because he along with Jim Watson, but Sidney Brenner I think was the main one who discovered messenger RNA. And messenger RNA is this thing discovered in like 1961, I think, when he was in Cambridge. And that's a messenger RNA is the thing that's being used to make two of the main vaccines that hopefully will end this pandemic that we're currently in. So messenger RNA, after its 60-year run, is now finally in clinical practice doing something interesting. But Sidney Brenner was the discoverer of that. Sidney was a lovely chap who I got to know in the last probably 25 years or so, a little bit more than that maybe. And he was always, he was a person who was, he grew up in South Africa, and he'd almost become a doctor. He actually knew, Seymour Papert also came from South Africa. I think they knew each other in those days. But anyway, Sidney Brenner was interested in computers and those kinds of things for very early time. And he'd been at King's College, Cambridge, which was the same place that Turing was at. And I must have asked Sidney Brenner this. I'm not sure that he knew Alan Turing. I know that Sidney Brenner was responsible for getting King's College to try and make a Turing archive. And I know I had always remembered that in Sarah Turing, Alan Turing's mother's biography of Alan Turing, she mentions towards the end of the book that when Alan Turing, towards the end of his life, did a bunch of, which he died in 1954, did a bunch of work on biological morphogenesis. And one of the things that Sarah Turing says is, he was getting these letters from all over the world, from places as far away as South Africa. And I was once having dinner with Sidney Brenner, and we were talking about Alan Turing, and he said, yes, he'd written to Alan Turing back when he was a student in South Africa. And I was like, that's by the way, did you know that in Sarah Turing's book, she mentions he got these letters? And so that was the letter that Alan Turing had received, was written by Sidney Brenner. But Sidney Brenner was always telling me, you should take all this computation stuff you figured out and you should apply it to biology. And there's something to figure out about sort of the computational foundations of biology that is more than just the story of genetics and DNA. And you should really figure it out. And he was he's kind of a very much of a sort of evangelist of ideas, and very much of a, if I hadn't had an awful lot of other things to do, he would have been very convincing that, that should be your research program. I mean, that was what he had done with things like the C. elegans nematode and its decoding and so on, a whole series of sort of great Sidney Brenner projects. But I have to say that in very recent times, I think I might have some ideas finally that it's a shame I can't talk to Sidney Brenner about anymore, because he was a person who, of all sort of biologists, I mean, he was always a bit frustrated that biologists weren't more kind of theory oriented, weren't more, let's actually imagine a formal theory and so on. Okay, let's, we'll come to Konrad Zuze. So Konrad Zuze was a German, technology person primarily. And I exchanged letters with Konrad Zuze towards the end of his life in the early 1980s, because Konrad Zuze had gotten interested in cellular automata and had this kind of generalized idea that maybe the universe was a cellular automaton somehow. And actually in a sort of somewhat ahistorical situation, because he had kind of, I think, thought about that in the 1940s. And but ended up writing about them in the 1980s after he'd read a bunch of things that I'd written about cellular automata. So it was kind of a confusing historical sequence because there was sort of some connection of things he was doing in the 1940s, but then when I'm seeing things he's doing in the 1980s, they're kind of after things I'd done. And so it was kind of hard to untangle what was happening when. But in any case, the earlier history of Konrad Zuze was during the Second World War. Konrad Zuze constructed a mechanical computer that was perhaps the first binary mechanical computer. And this computer has a very strange sort of story to it. Must have been 6, 7, 8 years ago, I was in Germany. Konrad Zuze was dead by that time, but his son, Horst Zuze, still alive. And there was at the German, in Berlin, at the museum there, at the technical museum there, there was a recreation of Zuse's computer constructed in World War II. And I met Horst Zuze at that time. Actually, I had talked to, this must have been beginning of the 2000s. There was a big kind of, a story of, did Zuze invent the computer? Was it, Turing, von Neumann, Eckert, Mauchly, kind of Atanasoff? Was it the American tradition, or was the computer really, was the computer really a German invention, so to speak? And this was sort of a, obviously it's a matter of national pride. I think it's a little bit like, the television. When I grew up in England, the television was a British invention by a man called Baird. After I've come to the US, it was an American invention by Sarnoff and people, I think. I think it's also a Russian invention and a French invention. So these sort of larger scale technology inventions, it's not clear they really have one inventor, but there was a period of time when there was a big enthusiasm for, Zuze was the kind of, the German inventor of the computer. So it was sort of, I'd been curious about this history. And so I had actually, that's right, I had talked to Horst Zuze on the phone, probably early 2000s, maybe 1990s, about this. And I'd asked him a whole bunch of things about, how much did Konrad Zuze know about Turing, for example? How much did he know about these other kinds of things? Horst Zuze didn't really know. So anyway, so eventually I'm in Germany, I'm at this Berlin museum, and we're looking at this reproduction of the Zuze's computer, built apparently in 1944-ish time frame, I think. it was explained that it wasn't quite a precise reproduction, but it was sort of close and so on. And what was were there any plans? Well, there was this one photograph of the computer that was sort of in situ at Konrad Zuze's parents' house from 1944 or so. So I said, so what happened to that actual computer? What happened to the physical computer? Well, it was destroyed by Allied bombing in World War II, was told. Actually, I think I knew that before. And I was like, okay, that's all well and good, but what happens to a metal computer in a house that's bombed? What actually happens? Did the house burn down? Did it, what was the actual, is there anything left? And so what then emerged was, well, actually, the computer was in the basement. And, it's like, well, okay, so then we did a little bit of research, I think, subsequent to that time, of looking for data on Allied bombing runs. And I think there was aerial reconnaissance that the British had of that area. And I think we were able to determine that, yes, there was that house. You could find a picture of it after the bomb fell on it. And then the question was where. That's right. When I was at this museum in Berlin, the key question I asked was, where is that house? The answer was, it's about 5 blocks from here. Unfortunately, I had a plane to catch, and I couldn't stay and go and explore that house. But the thing that we subsequently looked into this, and basically there was a whole question of the computer was in the basement, the house collapsed on top of the computer, what happened to the computer? And so I talked to some people who have done urban archaeology and so on, asked them about some of the issues with this. Things got a little bit more complicated because there was an air raid shelter that was nearby, and maybe the computer had been moved to the air raid shelter, maybe it hadn't. Zuze's parents actually had 2 adjacent houses. One of them is still a house. One of them has turned into kind of an open, well, was at that time an open space. Oh, by the way, I should say that these houses were on the western side of the Berlin Wall, just about 1 block from the Berlin Wall on the western side, actually in an area that at that time, after World War II and the Berlin Wall went up, was apparently a kind of a very dumpy neighborhood, though I think it's now quite a chic neighborhood. But in any case, so the computer, that first computer from 1944 or whatever, we still don't know what happened to it. And I had this plan for a number of years to sort of mount an expedition and try and, find excavate the computer. I kind of had this, it's sort of a thing that would be, I'd ask people, how does it degrade over time? It's made of steel, and what happens to that in the soil, et cetera, et cetera, et cetera. Basically, there should still be a bunch of computer left. But hasn't been excavated. And I think there's been, it's sort of a question of I'm sure it's it might be in the basement of somebody's house. And it's like, and it's then that becomes a complicated, I asked my urban archaeology friends, how does that all work? And, what do you do when it's kind of like an excavation that's like this thing, and, who owns it, all that kind of thing. But that can all be worked out. But I think it's sort of an interesting question. There's been a certain lack of enthusiasm about excavating this computer among people like this museum, and I've kind of found that a shame. And one of the questions is, what is there about this computer that might not be a thing one would want to find in today's world? And I think there's sort of a question. Well, there are a bunch of questions. In fact, I just recently learned from somebody who had known Zuze. Well, I should say that the subsequent history of Zuze. After that time, Zuze started a computer company in Germany that made initially much more simple, less sort of fancy kinds of computers as a practical, I think, more tabulating machines. And then sort of advanced to more elaborate computers. And there was, the Z1, the Z2, a series of Zuze computers. And I think that that computer, that company, well, in the end didn't make it, but I think it lasted for quite a number of years. And I was talking recently to a chap called Erwin Engeler, who's now in his 90s, who works at ETH in Switzerland, and had described himself as the first programmer of the first Zuze computer that was brought into Switzerland. And at the time, it was a big deal to get a computer into Switzerland, and it all had to be, I don't know, almost smuggled in there, and all kinds of complicated things had to be done. But it's so, you know, I think that there's sort of a whole swirling question of what was the relationship between sort of the German military effort and what Zuze was doing. And there are claims that sort of the original Zuze computer was funded, as one might imagine it would have been, by the German Air Force, interested in sort of aerodynamic calculations. Not a silly thing to do. But you know, then there are all kinds of questions about, you know, if you find the computer, what do you find stamped on the metal parts of the computer, and so on, and all sorts of, you know, history that one has to decide whether one wants to leave buried or not. And I think that it's so as it is right now, there's sort of a trailing question of what is the story of that computer, and, you know, how close is it to the recreation that exists in the museum? What can we learn from this one photograph that was taken of that computer? What do we know about what happened? I think that, and what do we know about what Zuze knew about what people like Turing had worked on? What was known, you know, in the kind of German military circles at that time, you know, about what was the amount of diffusion of knowledge. You know, there probably wasn't much from Bletchley Park and that whole effort, but, you know, Turing machines had been pre-Bletchley Park, although some, you know, many of the people who were involved in that, like Max Newman and so on, went on to have roles at Bletchley Park, and you know, it's hard to know what that mixing was. It's sort of an interesting little mysterious piece of history. All right, I think I should wrap this up. There's a question from Parmenides. Did I meet any rocket scientists like Wernher von Braun? I did not meet Wernher von Braun. I have to say, I will, oh gosh, what was his name? There was a chap who was one of the last remaining kind of German rocket scientists from that time, who, strangely, a young chap who actually works at our company now, but who I had met through our summer school, had been trying to get me involved with some initiative that was a space launch initiative. And this chap, oh dear, I can't remember his name. But anyway, just in a little bit of an exotic story, because this chap had some whole different scheme for producing rockets and so on. And the only place he'd been able to implement his scheme was in Libya as a kind of, during the Gaddafi regime. That was a place where he could actually, you know, try out launching rockets and things, and had done that for a while. And when that regime had fallen, he had ended up on some Pacific island. And so there was this rocket scientist, German rocket scientist, who had sort of been in the von Braun orbit, and then in the Libya orbit, and you know, just a very strange collection of things, who'd wound up on this obscure, you know, many airplane hops Pacific island, to operating a kind of a strange resort bed and breakfast type thing with a kind of German rocket scientist theming to it. And I had to say, I tried to persuade my children that we should take a trip there, but my children were unconvinced. So unfortunately, I never did it, and that chap died. So so I can't tell a good story about that. All right, we should wrap up here. Thanks for joining us, and thanks for lots of interesting questions. And there's a sort of almost infinite collection of these kinds of historical things to talk about, both in terms of somewhat contemporaneous things that people I've known, and much more distant past. And I'm being reminded that actually we have, I'm signed up. Gosh, I must be spending all my time doing these live stream Q&As. Tomorrow we have another live stream Q&A, science and technology Q&A for kids and others, and some of those questions about things like visual programming language that were asked here, I'd be happy to try and address there. I think in subsequent weeks, we're going to be sort of separating some of these live streams in terms of days a little bit more. This will be a series that alternates between, at least our plan is to alternate between history of science and technology, and business and innovation in alternating weeks. So anyway, thanks for joining us, and